Not, eating it? Yeah, all right. Hello everyone, welcome to Digital Media E10. So I hope last week was awesome and instructive. I certainly enjoyed watching the guest lecture, and I want to thank again Shelley and John for throwing that together and presenting that to you. Today is color and artifacts. And of course, before we get started, just a couple of quick reminders. This is the first week in a while where we don't have something due today in terms of the projects or the problem sets. Of course, the critiques are due every week, but we do have the problem set 5 due next week. And again, this was a 3-week problem set because some of the material from today's class is actually applicable to that problem set. So we want to give you time to actually use or to synthesize the information from today. And then the final project proposal is due next week as well. And so do start thinking about that proposal. It's not you don't have to write too long of a document. Really, one of the most important things that we want to understand is if the scope of the project that you have in mind is going to be sufficient. Is it actually going to be of approximately 2 of the numbered projects in terms of quantity of work, in terms of the scope of that project? And that's really what we're looking for. And do feel free to get started on your final project even as you work on your proposal, because it's extremely rare that we just outright reject an entire idea for a proposal. In fact, I don't think we've ever done that. But instead, we work with you to try to adjust the scope to fit our expectations, either ask you to tone it down a little bit or beef it up, depending on the amount of work that you described to us in the proposal. And so do get started on that. And even if you do miss the proposal deadline, please do send one to us anyway, because we want to know what it is that you're up to. And in fact, that's a requirement for submission of the final project. Is some point before you actually send us the implemented final project, we have to look at and approve a proposal, even if it's a few weeks late. So do be sure to take a look at that. And hopefully in sections, we've been talking about some ideas about final projects and sort of nurturing that discussion as well. So today we're going to talk about color and artifacts. And there's been a fair amount of discussion about color, at least about the color perception of the eye. And by a fair amount, I mean not very much at all. But today we'll get to beef it up a little bit when we talk about the way that digital cameras use color, that computers use color, and the way that we have to actually pay some extra attention to it to make sure that the color is consistent across all of your devices and all of the other things that come with this. But first, before we get actually into that, the reason that this is important is that the way that we perceive light, the way we perceive color, is very different than is mathematically or scientifically true. And so in other words, the way that we perceive it is biased based on a number of things. It's very hard to enumerate all of the things, mostly because I don't know them, but also because there's so much that our visual system is trying to achieve to try to represent the world in some way that's not just accurate, but useful to us. And a lot of things that have sort of come to play in the past few, maybe millennia worth of evolution is trying to make things make visual sense to us. So just as a couple of examples, I have some optical illusions here. How many of you have seen this one before? Nobody? Awesome. Cool. So this is like a tiled floor, and there's an object with a light source off to the right, and the light source has some light that hits the object and casts a shadow across the floor. Now you'll notice that there's 2 tiles that are in fact labeled. There's one at the very top labeled A, there's one in the middle labeled B. And the great thing about this illusion is that even when you know what it is, it still tricks you. So in this case, A and B, the tiles A and B are exactly the same color. So even if you know that, you might be looking at it and be like, no, that doesn't sound quite right. This isn't, I think you're making this up. Well, I'll prove it to you. Okay, so here's the slide, and I have this app on my computer, which comes with Macs, called the Digital Color Meter. What it does is it basically allows us to display color information, in this case red, green, and blue values from 0 to 256, or 0 to 255 in 8 bits, just like we've been talking about. Computers will actually display the color information. So here you notice that if I hover my mouse over this black area of the slide, it looks black, and so we see values of 0 for red, green, and blue. Over here, the kind of grayish area, or light grayish area, is this very light gray at 256, so on. Okay, so let's take a look now at this. So we have, I'll push this out of the way. Let's look at the color information for tile A. Notice that it's this kind of middle gray, 139, 139, 139. Now if I move my mouse down to over B, notice it's exactly the same value. Now you still may not be convinced. You may be thinking, okay, this is very carefully orchestrated plot to destroy my perception of color. So I also have this same image in Photoshop. Oh, where was it? Oh, here it is. Same image in Photoshop, and what I'm going to do is I'm using the eyedropper tool to pick up the color. This is the same value that we just picked up a moment ago, and I'm going to use a brush to actually paint that color from A to B. And now, hopefully, you can actually see that it is in fact the same color. Once we actually remove the shadow out of the way, then all of a sudden does this optical illusion become a lot more apparent. Pretty crazy, right? But this kind of implies some issues that we might actually have with color perception within a scene when we're actually trying to take a photo and we assume that it's actually some color, and then we might look at the image later and perhaps it actually appears slightly differently than we might have wanted or expected it. So this really just shows the context through which, because our brain perceives this area as in shadow, it actually is supposed to, our visual cortex actually provides some signals to us that says that this color information is actually different because it's actually in shadow than colors that are outside of the shadow range. But there's also other things that happen to our visual system as well. So I'm going to show you this image. And what I want you to do is to stare at this very center, at the black dot, and just do it for about 30 seconds. And I'll talk to you while this is happening. And I promise what's going to happen is nothing scary is going to jump out, no monsters, nothing like that. But in fact, what I'm going to do in about 20 more seconds is I'm going to change this slide. And the slide is going to look very similar. In fact, the image itself is going to be identical, except for the fact that all of the color information will be removed. And when I do that slide change, I want you to keep staring at the very center, the black dot. It'll be all aligned so that it's actually exactly the same. And without blinking, see if you can see how this image actually changes in appearance. Okay, ready? I'm about to change it in 3, 2, 1. Do you see? Blink and then look away and then look back. Did you see what happened to that image? What happened to this grayscale image after you had stared at that inverse color for about 30 seconds? Want to try it again? Maybe not quite for 30 seconds, but again, stare at the very center black dot for a few seconds. Really focus, channel your energies into this, and it's kind of a really neat effect that will happen as a result. Okay, I'm going to change it in 3, 2, 1. Do you see the inverse color? So what you actually see once I change the slide is the original color of the image, sort of superimposed on top of this grayscale image. And once you blink and look away and then return your eyes, you actually see that this image is in fact grayscale. So what's going on here? Well, in this case, we have our eyes get used to specific stimulus. And so very much like our eyes get used to the fact that we're in a bright room and it adjusts likewise so that we can actually see the light within that room, a similar thing happens with color. It gets used to the stimulus that you're providing to it in terms of the color, and it provides like this negative image of it, so that when I actually go to this black and white version of the image, we actually see those inverted colors. And then once we look away and blink and all that, then our eyes, or the cells in our eyes reset so that we no longer have that negative image that persists. And there's, of course, many, many illusions that exist. Here's another great one. This is just the This is an illusion called the Troxler's fading. And if you stare at the very center crosshairs and sort of in your peripheral vision, don't directly look at this blinking gray dot that's moving around. But if you look at the center crosshairs for long enough, what you will notice is that all of the color actually just disappears. You see that? It takes like just a few seconds, and all you see is this inverse cyan or green dot that is moving around the image. Do you notice that? Pretty neat stuff. And in fact, this is so prevalent, the fact that the tricks that our visual system play on us are so prevalent that every year there is a best illusion of the year contest. And there are significant numbers of entries every single year, and every single one tends to blow my mind. So this is the winner for this year, called the dynamic Ebbinghaus. So let's take a look at this one. This one's just a couple of seconds, I think maybe a minute long or so. But it is also, it has some text along the bottom, so do take a look at that. So this is standard sort of visual illusion where things look different based on proximity to their size. This is not necessarily related to color, but this is kind of a neat thing. All right, so we have a circle that appears to change size. Wild stuff. There's a few others as well. One of the other ones that I really liked back when I first saw it released was this, which is that it actually makes it's very difficult to describe. Things that appear to be the same are in fact not. So this is sort of an issue with our perspective, perhaps, or the way that we would perceive relative perspective in this particular image. Pretty interesting stuff. So anyway, let's come back to this idea. Now, with all of this in mind, we have to try to overcome these issues and try to represent our color accurately within our photos. So color, of course, is made up from the electromagnetic spectrum, wavelengths of light, and there's various ways of representing the full spectrum of color that we can actually perceive, and this is just one of them. This is a graph that is a chromaticity graph that shows us the possible types of colors, or the possible colors that we can actually see. Now, along the very outside of this graph, from this number 380 along the outside going clockwise through 520, 560, the greens, and then over here to 700, this is supposed to represent monochromatic light, meaning that there are wavelengths of light that if there was some source that was able to emit photons at precisely those wavelengths, these are the colors that we would see. It is essentially the purest form of color that we can see. There's no mixing of color to actually achieve that particular wavelength of light. And then everything in the middle are colors that we can perceive because it is a mix of one or more other colors. So for example, purple, what we would consider purple or violet, is in the middle here between red up here and blue down here. And so that is what the color purple is. It's actually a mix of these two colors. There's no single source of monochromatic light that can actually produce the color purple that we would find in the middle here along this linear part of the graph down here. Now, this is actually pretty interesting when you think about it, because this implies that in order for us to see certain wavelengths of light in their maximum saturation, that we need some source that can actually provide just that single wavelength of light to our eyes. And that's precisely one of the issues that we have, is that there are a great deal of things that try to produce color, such as our computer screens, for example, or our camera phones, or what have you, or our smartphones. But what they end up doing, because as you might recall, they have LEDs that are red, green, and blue only, they cannot, in fact, reproduce the full amount of colors that we can actually perceive. So we can try to define the space through which these devices will actually display accurate color. And there's a wide variety of these spaces. Some of them are theoretical, some of them are practical in terms of representative of what our devices can actually display to us. But one of these is, for example, the sRGB color space. So imagine that we have this graph that has all of the possible colors that we can perceive, and we're going to have 3 points on that graph representing a red, a green, and a blue, because that is going to be representative of the monochromatic light, the light that our computers can actually show us, our displays can actually show us. So that means that those LEDs are really the red, the green, and the blue LEDs at full brightness are really the full amount of saturation that we're going to receive for that color. So really they can't exceed the bounds of their design limitations, really. So there's a subset of all of the colors that we can actually see that are able to be reproduced by devices. Now, every device is actually different. The fact that we have this sRGB color space, which is really used, it's extremely common, it's really meant to try to unify all of the different devices with different capabilities in terms of color reproduction. But not all devices are actually able to show the entire sRGB space. Some of them will only be able to show a limited portion of even this limited amount of the full color gamut. Some of them can show a little bit more, but will shoehorn the colors that sRGB can actually display into their gamut, and then just not show other colors. So the way that we would get a mix of light is, of course, to shine these LEDs at specific illuminations to mix them into the various colors that we might actually perceive. There's a couple of, and so with this idea of an sRGB color space, we have this notion of mixing all of the colors together to get a specific value of white. So if we turn on all of the green, the red, and the blue, for example, then we know that we have some white value. But realize that white is kind of subjective, as you know. If you were to take a look at, if you were to read a book, for example, in candlelight, that light tends to be very red. But we would still perceive the page of the book as being white. And if we go outside during the middle of the day, for example, the color of the apparent color of the white would be very different, even though we would still perceive it as white. And so there's a similar thing that we'll get to in more detail in just a little bit when we talk about white balance. But there's a specific point in sRGB and other color spaces that defines white for that color space. The point has a specific name in this case. It's D65, which is in the middle there. And it really is just representative of a white value. They've just picked a white value and they run with it. They say, this is the white value of this color space. This is when your computer receives the value 255, 255, 255, representing white. This is the precise color value that you should actually display. And just to make this graph a little bit more concrete, realize that we have an x and a y value. Y is approximately the luminance. Notice that the greens are at the very top, blue is at the very bottom, and red is somewhere in between. And the x value, so along the bottom here, is the chromaticity, so approximately how saturated. So very in a similar way that we can think of different colors as having a specific brightness, if we were to remove that color, can we think of colors as having a certain amount of saturation just by looking at them? And red, to our eyes, tends to look extremely saturated. So that's why we have this particular style here. This is trying to replicate or trying to acknowledge the human visual system on top of the way that colors actually exist in the world. So anyway, coming back to this idea of having these color spaces, we have the red, the green, and the blue outer points defined, and anything that we can replicate within those values is only contained within this triangle. it's actually not possible to replicate colors outside of that triangle within this particular color space. So you'll notice if we take a look at this, there's perhaps quite a lot of area that's missing from this color space. There's a lot of the cyans, the greens in particular, are really missing from this color space, and that's kind of a limitation, perhaps, of this particular definition. Now, with that said, realize that sRGB is the most common color space, and we'll talk more about what that is and what it means. But even though I'm going to show you another color space, realize that this one is sort of the de facto standard. By default, you can assume that your phone, your computer, your printer are operating in some form similar to the sRGB color space. But coming back to this idea of having very few greens represented by this color space, there is another color space called Adobe RGB that tries to extend a little bit into this green area to try to represent more colors. But realize what's happening here is that what we are saying is that we still have values in our image from 0 to 255, but basically the way that we can think of these values is that it's kind of like a paint-by-number system. What the color space is doing for us is telling the computer that when it receives some specific value, it knows precisely what color it should actually output to the user. So what that means is if I have a value of 255 for green and 0 for red and 0 for blue, I should see just a purely saturated green. And those greens should technically be different in Adobe RGB compared to sRGB. So we're not changing the values. We still have 8 bits worth of value in our images, but by applying a color space to those values, we're basically changing the palette in a way of what the colors that will actually be displayed by the computer. That's how it should nominally work, is that the computer should know precisely, given the color space information, should know precisely what a value should look like and will display that to the user. But there's a lot of issue with this, and there's a lot of additional complexity that actually goes into this. But before I get into that, I do want to show you the vast array of color spaces that we actually have. So Adobe RGB and sRGB are extremely useful to us as photographers, but there's in fact a wide variety of other color spaces that exist as well. So here I'm going to bring up this other application called the Color Sync utility, which is also included with Macs. And we have a graph down here which we can actually change to YXY to approximate what it is that's the same sort of graph that we were looking at just a second ago. It's not quite zoomed out enough for us here, but we can sort of get a sense of what's happening with the color space compared to the full gamut of colors that we can actually see. And if I change the color space to look at some other ones, for example, let's find sRGB in this list. So scroll down. Here's sRGB. We can see that it, in fact, has a smaller gamut compared to, or a smaller number of possible representations compared to that Adobe RGB. But let's take a look at some other ones as well. NTSC is an old television standard, and it was supposed to represent far more colors in its color space. Now that might or might not be true, whether or not it was actually able to achieve that, but that was in fact the color space that was applied to it. So let's see if I have something else like the color LCD. This one is actually pretty interesting because this implies that my computer, it has a color LCD, has a display that is able to produce a certain number of colors. And so we could represent those possible colors with a color space. And so that's kind of what we're seeing here is the possible color space represented by my laptop screen. In this case, this is not the calibrated version. The calibrated version, in fact, looks like this. So the way that my computer came initially was with this color space with a wide array of colors, but that was found to not actually be true. When I used the hardware device called a colorimeter to actually I used that device along with some software and asked it to try to figure out what precisely were the colors that my monitor was able to represent. We noticed that it is able to represent a far smaller space than originally intended by the manufacturer. And in fact, monitors change over time. Even if you get a monitor that's a fantastic quality and has a wide color gamut, as the monitor ages, it in fact is able to reproduce fewer and fewer colors. But we'll get to more on that in just a minute. So just to sort of make this idea a little bit stronger here, there's the color LCD, which is the original color profile that came with my computer. I'll hold that for comparison and compare it to the actual proper color calibration of my machine, which of course is much smaller still even compared to the sRGB color space. So there's a wide variety of profiles and color spaces that might exist for a computer. For our purposes, we care mostly about those two color spaces that I had mentioned before, sRGB, and if you are printing, perhaps you care about Adobe RGB. Perhaps if you're doing professional printing, or if you have a printer that has more than 3 inks, then you might use even a different color space, or even like a CMYK style color space where there would be 4 points instead of 3, because you have 4 inks to actually represent the various colors on your machine. So what does all of this mean for us, practically speaking? How do we actually use this to make our photos better? Well, realize that there's a whole chain of items, of devices that are used when you are actually creating a digital photograph. One of them, of course, is a camera, and the other one is most likely a computer. So if we simplify the whole chain just to these two devices, this is essentially what is happening. We capture a photo with our camera, and hopefully it's properly calibrated by the manufacturer to actually know precisely what color information was read from the sensor. And then it will convert that into those values, those 0 to 255 values for all of the different colors, and embed within it a profile saying that this value represents this color. And because our device is talking in a specific color space, we know when we read this file, in particular when our computer reads this file, like Photoshop or Preview or whatever application you're using to actually view this image, it knows that those values represent some specific color that it wants to display on the screen. But realize that there's even more to this chain here, because we have this paint by numbers sort of system where we have an image file that has a specific color in the very first pixel and another specific color in the second pixel and so on. And the computer is able to interpret that, to know that that specific color is supposed to represent an actual color that it should display to the user, but it still has to tell the monitor, it still has to tell the display that it actually wants to present that color accurately. And so this is where the idea of color profiling becomes really, really important, is that your computer probably understands, given some software that is properly able to understand color space information and the embedded profile provided by your camera, it knows precisely what color it's supposed to display, but it may not actually know if the monitor is correctly displaying that color value. And so what color profiling does, excuse me, is that it notifies the computer when it sends a specific signal to the monitor for a given color, it knows precisely what that will produce. And so there's a wide variety of techniques that you can actually use to profile your monitor. There are some purely software-based solutions where you sit in front of your computer and it displays some colors and it displays some hatched lines and it tries to get you to change some sliders, and then you have just visually profiled your monitor. And that works. It's perhaps better than nothing, but it's not really that accurate. Because, especially when you're using a laptop or especially nowadays, now that most of our monitors are flat screen, they're not the CRT style, changing your angle to the display actually slightly changes the color that you perceive from that display. So changing your viewing angle, changing the amount of ambient light will actually alter your perception of the color that's being given by your monitor. So unless you're able to reproduce that exactly every single time, doing it purely visually is not necessarily going to give you the best quality out of your profile. So you can use some hardware. So I'd mentioned before that I happen to use like a hardware device that actually allows you to profile your monitor specifically. Unfortunately, these devices tend to be somewhat expensive. They tend to run a couple of $100s in order to get a good calibration system. One of them is the one that I used before was an X-Rite color profiler. And this is actually like a little device that you rest on top of your monitor, and then it has some software that displays color on the monitor, and the device actually captures the color and records precisely the value that was output by your monitor. It does that for a wide variety of colors, and then it knows. It's able to tell the computer through a profile which tells your computer precisely what your display is capable of. The computer is then able to finish the chain. It's then able to take an image that has some values in a given profile, and it will know the value of the color that it's supposed to display at every single pixel, and then it will know how to translate that into a signal that your display can then show properly. And so this way is really the only way that you can be sure that the colors that you're looking at on your computer are absolutely correct. And once you've started calibrating your displays, you'll actually start to notice that while many displays are actually pretty good, I mean, they're not super terrible, they're actually not that great. You'll notice that in grayscale images, for example, certain shades of gray will look a little bit more green or a little bit more red. You'll notice that some of the contrast, especially at the very dark regions of images or the very bright regions of images, you may not able to differentiate between the darkest shades or the lightest shades compared to a properly calibrated monitor and other such things. And these actually end up being pretty important when you start working on these images for print or for actually displaying them in some sort of professional or even somewhat professional setting. So calibrating your monitor can be really, really important for this purpose. But if you're just going to send your photos to your family, for example, and you're just going to display them on the internet, chances are most people that view your images aren't going to have a properly calibrated display. So maybe it's not quite as important in that context, and using something like a software color calibrator would actually be just fine for your purposes. Getting at least something out of it would perhaps be better, but maybe saving the money and not getting a full-blown several $100 color calibration system isn't necessary unless you really feel like it's necessary for your particular workflow. Any questions on this? Okay, so we have a color space that defines a sort of a paint by numbers system where we have values of 0 to 255, and the color space defines what those values should be, what colors those values should actually represent. The computer is able to interpret that and understand it, but it needs a monitor profile. It needs profiles to actually understand. So the computer will say, okay, I want to display this color, but I need a profile in order to actually properly display it on whatever attached monitor there is. So there's multiple steps in this chain that are actually somewhat important when you're actually working with photographs like this. And it's also important to realize that, like you saw with the color sync information from my laptop, for example, it wasn't able to actually reproduce all of the possible colors for sRGB. And that's especially true for color spaces like Adobe RGB. I don't know if there's any reasonably priced monitor, or if there's even any monitors, period, that can actually display the full color gamut provided by Adobe RGB. Perhaps there are, but it's actually somewhat difficult to achieve. The reason that you would want to use it, though, is that you would want your your photographs of a landscape scene, for example, that have a wide array of green colors to actually display in as accurate way as possible on a print. That might be one reason why you actually want to use this. So there's this notion of needing to be able to have color spaces and actually convert between them. Perhaps you have an image in a specific color space and you actually want to convert to another color space. So perhaps you set your camera's color space to Adobe RGB, for example. And by the way, many cameras actually do have the option of embedding a specific color profile within the image file. Most of the time, by default, it's sRGB. But sometimes you can actually change it to Adobe RGB if you want it to capture that additional color information. Or that's somewhat incorrect to say. If you actually want to more properly replicate the possible green colors out of the scene, you might want to switch it to Adobe RGB. But then if you decide later on that you actually want to display this image online, that perhaps it would be better to actually convert this color space from Adobe RGB to sRGB so that you can then accurately show some colors on the screen. So there's this idea of gamut mapping, which does precisely this. And there's a variety of techniques of gamut mapping, but for us as photographers, we really care about two. And those are these, the perceptual gamut mapping and colorimetric gamut mapping. And for the vast majority of cases when we're dealing with photographs, we're going to want to use perceptual, because this maintains the same perception, or as much as possible, the same perception of gradients and colors from one color space to the next. In other words, if we have a large gamut like we would in, say, an Adobe RGB color space, we want to convert it to a smaller gamut like in, say, a sRGB. We would want to shoehorn all of the gradients into the possible gamut for sRGB. So this is almost all of the time what you want in terms of digital photography. But there's also colorimetric, where if it's actually important that you preserve the color values as they are, you can essentially throw away that extra information. You can think of it sort of like clipping that color information away and preserving the portions of that gamut that actually exist in both of those. And so that's a lot of the colors when we're talking about sRGB and Adobe RGB. In particular, the red and the blue values will largely be identical. I believe that that technically the red and the blue are exactly the same point in, sRGB as they are in Adobe RGB. But really, this is probably more of a scientific endeavor if you really wanted to preserve the raw, true color information when mapping from one gamut to the next. Now, why is this actually important? We'll realize that when we're dealing with color management, we are actually displaying most of the time our images in sRGB. And for the longest time, for many, many years, web browsers, up until probably, honestly, last year or maybe this year, I think now most of the major web browsers actually have proper color management support, where when they're looking at an image, it will, in fact, take into account the embedded color profile. For many years, what we would see in just about every popular web browser, you name it, it probably didn't support proper color information. So what this meant was that if you had an image in Adobe RGB or some other exotic color space and you tried to display it on your web page, the colors would actually just look totally wrong because it would interpret those numbers as some other values. The paint by number system would fail because you intended it for one palette and it was actually displayed in another. And there were a lot of really interesting examples of this where people would actually invert the color space a little bit. They would actually define the color space as red being green and green being blue and so on. And so you would actually get, in these web browsers that did not have proper color management, you would see inverted colors because that paint by number system failed and it was totally ignoring the mapping, the color space, which defined what each value should actually be. But nowadays, Safari for many years has been the winner in color management. If you're using a Mac and using Safari, even since I think 2008 or 2007 or something, you were safe. It was actually able to display the color information properly. Chrome, I think, followed a few years later, but still it was like maybe 2011 or something like that, and or maybe it was even Firefox. But now I think those major ones are doing it, and who knows what Internet Explorer is doing. I honestly have no idea if Internet Explorer is properly showing color information to you. But what I'll do during the break in a little bit is I'll try to find some web pages that actually display some color information or displayed some images with kind of wacky color values, but with the color space that would fix that information so that it would actually look appropriate in a properly color managed environment. And we'll test some browsers on my computer to see if that actually works appropriately. Okay. Now, there's one thing that I do want to show with regards to this, this gamut mapping. We can understand perhaps a little bit more about Photoshop's color information. So here, let's see, I just want to show you. Let's see if this will work now. And no, let's see, I need to do, here it is, Photoshop's color settings panel. So if you've used Photoshop in the past, perhaps one of the scariest things to look at was the color settings panel in Photoshop, because it was kind of, if you didn't know much about color spaces, it was really difficult to get through all of the options that are here. And in fact, a lot of these options still don't really apply to us, but we can take a look at some of these and try to figure out what some of these actually are. So notice that we have here this section in the upper left called working spaces, and this basically defines the color spaces that we want by default for when we're working with photographs in Adobe Photoshop. And by default, you almost always want to use sRGB because, again, that is the most widely used color space and the most likely one to appropriately display your photos when you're submitting them online or submitting them to your friends. But you can, of course, change that to any one of the other popular color spaces as well, like Adobe RGB or others. Now, CMYK is one you would really worry about only if you were dealing with print. But the standard for that, if you have a printer or a lab that asks you to define a CMYK color space, they probably will tell you precisely what profile or what color space they would want to use. So the default for that is generally fine. Then there was always this other scary question that it would ask. If you would open an image, for example, and it would give you some weird color space error, like you open an image from the web and it would say, this image doesn't have a color space, what do you want to do? It was very common to just kind of freak out and just click cancel or something, or click something to actually get the image to open. But now we can sort of understand just a little bit better what it was asking you to do. So imagine that you have an image and it doesn't actually have an embedded color space information within it. Well, we can sort of guess. That means that it has all of the numbers available in display, but that connection, that mapping between what those numbers mean to the actual color value is not in fact there. Now again, most of the time for images that do not have the embedded color space, we can sort of assume that sRGB is going to be the correct one. So we can apply perhaps an sRGB color space to that image that didn't have an embedded color space, and most of the time, 9 times out of 10, will it be correct. So you can sort of assume that that's kind of going to be your default position. Now, if, for example, you have a file that was created and has an embedded color space, so when I say embedded, I mean this is literally some information that's embedded within the metadata. So we talked about the EXIF metadata and all of these other things. One of the things that can be embedded within these images is also the color space information that acts as this mapping from the numbers to the colors. But sometimes if you have a default color space, for example sRGB, and you're opening an image in some alternative color space because it has an Adobe RGB color space embedded within, for example, then Photoshop will ask you what you want to do there. And generally what you want to do is to preserve the embedded profile. And the reason for this is that if you were to convert it to some other profile, perhaps it would then open in sRGB, which is, again, the working RGB is the one that we had set at the very top, our working spaces. So it would perhaps convert it to sRGB. But generally, if I'm opening a file at least in my case, if I'm opening a file that I've downloaded off the internet, for example, and it has an embedded color profile, I want to see that image in its intended way. And so I actually want to open it with its preserved color profile. And so I'll tend to preserve the embedded profile. Now, the default for older versions of Photoshop were all of these things were checked. Missing profiles, it would ask you when it was opening. If there was profile mismatches, it would ask you when it was opening. Profile mismatches is when you have working space that was different than the embedded color space. Or similarly, when you were pasting it. And these would cause the sort of scary prompts that most people tended to ignore. And so it seems like Adobe has finally caught on and unchecked by default all of these things. And you can still get that back if you want it. Now that you understand what's going on, hopefully understand better what's going on, you can get that feature back by checking these ask when opening. But usually it doesn't really seem to be totally necessary. Now the rest of these conversion options, for example, in this case, relative colorimetric, we were just talking about relative color or colorimetric versus perceptual. In this case, we might want to select perceptual as our default, but it's pretty rare when I actually do color space conversions. And the rest we tend to, the rest we can actually somewhat ignore. We'll actually talk about, so there's the second option here, use dither. We'll talk about what that actually means. Actually, we can talk about it now. So the color space, of course, defines specific colors that the computer should display to you for a given value. But as you saw, especially with my monitor and with your own monitor, almost certainly, your computer is not actually able to display all of the possible colors in a typical color space. So what a computer will do is and what some software will do, like Photoshop, is it will try to trick the monitor into actually displaying that color by using dithering, which is just a technique that alters neighboring colors just slightly so that they mix slightly differently and it actually appears to be a slightly different color. This is perhaps fine for our case because then it improves our perception of that out of gamut color. And it probably isn't going to necessarily be bad. But if you need absolutely the most accuracy out of your monitor setup, then you probably want to uncheck use dithering. And the rest, again, we can pretty much ignore for now. Any questions on this stuff? All right. So we talked about color spaces and how we can embed color space information into images, which is almost always a good idea because if your web browser, if your user happens to use some software that is actually able to understand that color information, that embedded color space information within your image, then you're sure that it will be reproduced as accurately as possible on their computer. Otherwise, most likely what will happen if you don't apply color space is that the computer will assume sRGB and try to display it in sRGB, which might be fine normally, but perhaps not depending on your particular circumstance. And as a result of having these different color spaces, we might actually want to map between the two. So we have this concept of gamut mapping. Gamut is really just a fancy name for this color space. And we might want to map from one to the next using a variety of mapping techniques. But for our purposes, perceptual or colorimetric are the ones that we would probably use. Perceptual or relative colorimetric are probably the ones that we, in fact, would want to use. So I talked a bit already about monitor profiling and color management, but I did want to mention a couple of other things about this. There's different types of monitors, of course. So there's the obvious kinds where there's the flat screens, the kind that we have in laptops and TVs nowadays, and then the old school, really big fat ones that were huge on your desk and made your desk slump, or at least makes my desk slump because it's not very good. And there's a wide variety of other ones as well. But even within these flat panels, even within the context of these flat panels, there's different technologies. And these different technologies have different color reproduction capabilities. So there's the one that you typically will find as the one that you want is what's called an IPS display or an SIPS display. And this display is the one that happens to have the most color reproduction possible. And nowadays, we're finding that a wide variety of displays that we can purchase are, in fact, IPS displays. All Macs have had them for many years. A wide variety of PCs now are also including IPS displays in increasing frequency. But about 10 years ago or so, it actually made a big difference. Sometimes you would hear about this display called a TN display. That was just terrible. It had no contrast, had no color. And fortunately, we were moving away from all of that. But you generally want to find, if you're working with photographs, an IPS display. Even so, the desktop panels, the panels that tend to be used in the larger monitors that you would actually have at home, can actually be higher quality and be higher and have better color reproduction because of their power requirements. Because they can actually be plugged into the main power line, then they can actually use a little bit more power. They can be a little bit, I don't know if less efficient is the correct term, but they can actually spend more power being a little bit brighter, displaying some more colors. So generally what we find is that even so today, our desktop monitors tend to be higher quality than our laptop monitors. And believe it or not, there's actually a number of monitors that cannot display full 8 bits worth of color information. So all of this color space data aside, they really can only accept 6 bits worth of information, which is really, really terrible. That's again, not 256, that's 8 bits. That's not 128 because that's 7 bits, but we're talking about 74 distinct values in the red, the green, and the blue. So they would do a lot of this dithering to try to reproduce the color information. I think nowadays, though, fortunately, in 2014, we're seeing fewer and fewer of these, but I bet that a number of laptop displays remain 7 bits or so, not able to actually display all of the possible colors. All right, so with regard to color management, there's a couple of other things that is important to keep in mind. One of them is this concept of gamma. And for our purposes, we can really think of gamma as being some measure of contrast, but it applies to your entire monitor. It's set by the system, it's set by your color management system within your operating system, and it actually defines how much contrast, essentially, your computer has. And this is an old term from back in the day when we actually wanted to, when we had those tube-type TVs, and we needed to, the way that they actually functioned by shooting the electrons onto the phosphorus screen was not quite accurate linearly, so they had to compress it with gamma. There's a bunch of history behind it that we don't really need to care about too much, but the system still exists to this day. And I mention it only as a warning for those of you that happen to be using older Macs in particular. Many older Macs that have an operating system of 10.5 or below, Leopard or older, had a different value of gamma than the newer Macs and all of the versions of Windows. So the standard gamma value that I recommend you set your computer to is 2.2. Older Macs had a much lower value of 1.8, which means that things look slightly less contrasty. And this did make a bigger difference a few years ago when people were much more likely to be running these old versions of Macs. But it was extremely frustrating to get the contrast and saturation just right on your image and then look at it on another computer, like a Windows computer, for example, and all of a sudden it just looks overly contrasty and overly saturated because of this difference in gamma. So when you're actually doing a color profile on your monitor, it will generally ask you your target gamma, set it to gamma of 2.2, and that's probably the default, but just to be safe, set it to 2.2 and you should be good to go. It is worthwhile to note, however, that some computers do come with slightly higher gamma, which means that you might get your contrast just right on your machine, but then you would look somewhere else and it would actually look slightly less contrasty than you would want. So as you're doing your color profile, set it to 2.2 and you should be good to go from there. All right, so if we talk about, when we're talking about color, it's also important that we talk about, oh yes?
How does gamma affect when you're printing? Does it affect it all? Do you still want to do it? Would be better to work with a higher gamma if you can?
So generally, if you're doing pre-press work, I believe the gamma is actually set slightly lower, some value like 1.8, which I think was the reasoning behind old Macs having a gamma value of 1.8. I think gamma, so the contrast that you are that your printer will display probably depends on a wide variety of factors and may not necessarily have some specific gamma value that we can sort of distill easily in class. But I would wager that most printers, especially that you would buy nowadays, would actually come in such a way that you would be able to print out something and have it look as identical as possible to a properly color managed sequence of production on your computer. But I bet if you were to work with a professional grade lab or some other professional means of producing some prints, then you probably would have to pay attention to this a little bit more. And in fact, that's sort of useful to think about, because it might actually be the case where when you print it that it looks a little bit more contrasty in the print than you might have wanted. And sometimes setting your monitor's gamma to a lower value like 1.8 might try to mitigate some of those issues. Okay. So the discussion about color is not really complete without, of course, color temperature. And it's really, the idea behind color temperature is that it really deals with the temperature of some object. So you've heard the term glowing white hot, glowing red hot, these sorts of things. This is actually a true physical phenomenon. When there is an object and it has a certain amount of heat, it emits some electromagnetic radiation in a given spectrum, and so it actually does give off some color. Things that are hot enough to actually produce color in their electromagnetic spectrum. And so as things get hotter and hotter and hotter, they go from red all the way up to blue and so on. And so there's this interesting dichotomy, because culturally speaking, we think of the color blue as being a cool color. And we think of the color red as being a warm color. But physically speaking, that's not necessarily true. As you probably know, if you have a red flame, it's not going to be quite as hot as a blue flame. Blue flame is going to actually be a much hotter temperature. And that is actually represented by this idea of actual color temperature. So when we're talking about color temperature, we use the measure of kelvins, which is actually a measure of temperature, to determine the distribution of color given by some particular object. So our sun, in the middle of the day, for example, emits a certain spectrum of light, and our atmosphere actually allows that certain spectrum of light to fall through. And so in the middle of the day, we see an apparent color temperature of about 6,500 Kelvin or so, give or take, depending on a number of factors, including overcast and where you are on the Earth and altitude and so on and so forth. But about 6,500 is pretty reasonable for midday. But as we go inside, for example, if we're in incandescent lighting, or especially if we're using candlelit lighting, where the color the actual temperature is much cooler, that means that it gives off redder light instead. And so the color temperature has actually dropped. The actual temperature itself has dropped significantly, producing more red tones. Again, remember this dichotomy that there's red hot, which is a cooler object, and blue hot, which is actually much hotter of an object. So the sooner you're able to sort of let go of those, or distinguish between the cultural phenomenon of naming blue as cool and red as warm, the sooner this will hopefully become less confusing. It's just unfortunate that we have this actual dichotomy between these distinctions. So realize that it's really just the whole concept is really just this glowing object that actually gives off a certain spectrum of color, and we are perceiving that color based on the wavelengths of light that we are receiving. And if we were to actually apply this onto that same graph, we can actually see how color temperature moves into this sort of blue realm. And so we have very cool colors are really warm over here on the far right. And then as we go left along this line, the temperatures are actually increasing, and so things become increasingly blue. Now what this means is that we generally want to try to capture a photograph in the exact white, in the exact color temperature that might represent that scene. Because remember, when we're dealing with color spaces, it is going to display white at this particular value, D65. And so in order to actually represent that accurately, we have to have this white balance that actually defines what value is actually going to be white. So based on the lighting that's in the room, there's some spectrum of light that's actually being output by whatever our source of illumination is, and we want to try to capture that using this color temperature to define what should be white and then be able to reproduce that accurately on our computers. So you can generally set this manually on your camera, but that is really difficult in changing circumstances. If you're outside, for example, with changing light, especially if there's any clouds that move in, or even just even as the sun changes after a few minutes, the color temperature will change because the atmosphere is absorbing different quantities of that spectrum of light emitted by the sun. Using it outdoors is very difficult, but if you're indoors and you're using lights that have very known quantities of emissions, then you generally will want to set your white balance to something very specific that actually matches the output of your lamps, and set it and forget it. Basically, just continue using it in a very consistent way. Now, what this means, though, is that for most of us, we tend to take photographs in changing situations. Unless you are doing a lot of work in a studio, this is probably going to be it's probably going to be the case that you will in fact need to change your white balance after the fact. And what this means is, fortunately, when you actually use a RAW format, you can actually do this. You can actually go and in post-production change what each of the values actually represent in terms of their white balance information. When we're using a JPEG, unfortunately, the camera decides automatically what the color balance should be, what the white balance should be, and will set that in and solidify it in the values represented by the JPEG. And so, as we've talked about before with posterization and other things, this isn't necessarily the best thing for us. So generally what we want is, there's a variety of techniques to overcome this. In software, typically you will have the opportunity to use a little eyedropper tool and try to pick a middle gray. Generally, there is going to be some pixels in your shot that do represent some sort of a middle gray or even a white or like a black, and you can use that to represent that value, and it will be able to change the white balance based on that selection. Sometimes, though, it's not possible. Perhaps you're in an extremely colorful situation, and one of the things that you might want to do is to first take a picture of just some white object and reflecting the light that actually exists within the scene, and then you can later use that, find the color temperature from that, and apply that to the rest of your images as appropriate. Okay, let's take a quick 5-minute break, and when we come back, we will continue talking about artifacts. All right. Hello, everyone. Welcome back. So before the break, we were talking about color and color spaces and profiling information. And I was making the argument that color profiling is really important, and it's especially important if you want to have a consistent look of color across your own computers, across your own devices. You actually want to be able to accurately display color information or the color in your photographs to your friends and to your family. And there's a couple of ways that we can sort of hammer this point home, and one of them is to actually talk about color in the context of white balance. And right now I assume that for my purposes I'm using an sRGB workflow, and I have my monitor properly profiled. In this case, we're using a projector, and it's totally not profiled. In fact, it's probably very inaccurate. And but assuming that I have all of those pieces in place, I can now look at the color that's being presented to me from my software, in this case Lightroom, which is hopefully taking the color space into account from my camera and actually displaying the color information that I want appropriately. So this is a photograph that I took last week while I was having fun in Ireland while you guys were here watching the guest lecture. I will admit that while the guest lecture was happening, I was not actually having any fun at all. I was in the middle of a conference and slogging through it. So this is really from the weekend where I rented a car and went out into the countryside to sort of appreciate the country a little bit more. And this is from the cliffs of Moher. And unfortunately for my coworker who was with me and my sister who came up to visit me, it was that time of day where the light was starting to get good, but it wasn't quite there yet. And despite what it looks, it was really cold. I mean, the wind was just blasting across the Atlantic, and it was super windy, and it was like really cold. And my sister and my coworker were just huddled and shivering. And I just said, "Hold on, just one more picture for probably about half an hour." So there's a few pictures here. So there's this one, and it's not meant to be like oh, look at my fantastic photos, but instead to show you these two images and sort of look at the differences between the two. There's some obvious ones in composition, but look at the context of these in terms of the color. So the light is being reflected from, the sunlight is being reflected from the greenery here, and we get a specific look in the color of how that image actually looked. And I do want to point out the white balance, which we can change here. So this is one of the very first things I tend to do when I'm looking at these photos is to adjust the white balance, make sure that it actually looks good. And in this case, I think the white balance is actually pretty appropriate. You can kind of look at there's a variety of contexts to look at here. One of them is the clouds in the sky. Notice that the clouds do appear to sort of be fluffy and white and gray and sort of not have any sort of unnatural cast to them, unnatural blue or unnatural warm cast to them. And so the other color is probably correct as a result, but if it wasn't, then I would perhaps want to change my color temperature to either be warmer by increasing the relative color temperature or cooler by decreasing it. And we can sort of compare that to another photograph which happened a little bit later, and notice that some of the color is actually changing here, but really the color information or the color that's changing is not necessarily that on this sort of castle, but it's starting to become warmer overall. Just as the sun was setting, the light was in fact becoming a bit warmer, and the color temperature did in fact go up slightly. But we can sort of see what happens if I actually make those changes. Generally, what I like, especially with sunset, is to just increase the color temperature just a little bit to make those colors pop just a little bit more. But perhaps that's something that you will want to decide for yourself. And especially you don't want to change it to such a degree that aspects of the image that should be white, such as the breaking waves at the bottom or the clouds at the top, are no longer truly white. But that's just one of the things to actually take a look at when we are dealing with color. So we have the color slider, but most of the time what I probably use is this eyedropper, and I find some region of the image that I know should be a proper white or a proper gray, and actually select that and see how the color or the white balance for that image actually changes. In this case, it actually increased it just a little bit, and this actually looks pretty good. It's a nice amount of warmth in the color being reflected from the cliffs, and and the color of the clouds and the breaking waves at the bottom does appear to be somewhat gray. And so there's probably differences in play here between the projector and the color information. That should be the color profile for this projector that should actually properly display this color, but it is what it is. Yes?
So like the optical illusion where you stare at it for a while, and
Yeah.
you flip and you see the inverse because your eyes adapt.
Right.
Do you find when you're playing with the white balance here that you have to like look away for a while and then look back?
When I'm editing photos, I'm constantly looking away and then looking back, especially if I'm for the very same reason as these illusions, actually, like you were talking about just a moment ago. Changing the contrast, just staring at the image for too long, it's probably not the same response as the illusion itself. The illusion is would be persistent. If there was some aspect of this image that was actually causing my color perception to actually change for that image, that would be persistent no matter how much I kind of like look at it and come back to it. But certainly there's an element of editing fatigue that comes into it, and looking at an image for too long, I get an idea of how I want to actually represent that image, and after making the modifications to it to what I think it should be, sometimes leaving and then coming back, I actually will find that I've overdone some element of it because I had grown accustomed in some way, and again, not necessarily in the same way as these illusions, but I've grown accustomed to it in some way and needed to just take a little bit of a break and come back to it with a fresh start. So this is perhaps more of like a psychological sort of element than an actual physiological component.
Well, just the physiological effect of the white balance shift, because like you said, when you're reading by candlelight,
Mm-hmm.
you look at a book page and your brain still says this is white.
Right.
So if you're looking at the image and it was at 5600 and you're looking at the waves and you're like, these are white. And
Right.
then you use the eyedropper and the eyedropper says, oh, well, actually this is white. Do you ever find that when the eyedropper does that it looks wrong to you at first?
Oh yeah, certainly. I do certainly find it to be the case where if I use the eyedropper on a part of the image that I know should be gray, it will look wrong to me at first because I had grown, in fact, accustomed, perhaps in some physiological way, to the colors that were displayed before. And there's other things at play as well, such as the ambient light in the room. I think that can have an even more drastic effect on my perception of what the color balance should actually be for this image. I have some lights behind my computer monitor at work, and they're the kind that can display all sorts of fancy colors. And usually I have something kind of bright to keep me awake or something. And I noticed that if I edit a photo in that context and then change the color, it will just look so wrong. It will just be so completely off because of my actual physiological reaction to the ambient light that was actually really impacting my ability to edit the photo properly. So yes, I think that using the eyedropper, there is some element though that you might click on an image, on a portion of the image that should be middle gray, but you might actually miss those pixels and actually select a pixel that for some reason or another, due to camera error or due to noise or something like that, is not actually properly gray and might actually be a red pixel, for instance, and then it's actually totally off, and then that's actually wrong. And that can happen in a more subtle way as well. So generally, I will kind of select a variety of areas just to be doubly sure, just to see if I'm able to consistently get the same white balance. And we can even sort of see that now that you've been sort of staring at this one image with this one white balance for a little bit. If I go back to the one before, it might actually look, and so this is a very small change. We're talking about a change of only 800 Kelvin or so, or 900 Kelvin or so. But even now, this one sort of looks wrong to me. Now it just looks too cool. It looks like I've actually changed the color temperature for the worse. Okay. All right. So let's come back to the slides here, but let's switch gears a little bit. And we've been talking about color up until now, which is hopefully you're getting the sense that it's really important to have a properly color-managed sequence of processing so that you can actually properly display your images. Oh, I forgot during the break to look up that one website that has the cool demonstrations of improperly managed color browsers. And maybe if I'm able to find that, we'll tweet it or something. But I did want to switch gears a little bit to artifacts. And there's a wide array of artifacts that might actually exist. There's sort of a spoiler here in that we could talk at length about all the different types of artifacts, and we could spend some time talking about ways that we could actually overcome them. But I can tell you right now that a lot of the ways that we can overcome the artifacts is simple, is that we'd use the center part of the image. Generally, the corners of the image are going to have the worst representations of artifacts, and also that we stop down the aperture. Using the lens at its maximal aperture is actually going to show the most amount of artifacts. So those two things are really the way to solve the problems that we are about to see. And unfortunately, that's not always an option. Sometimes you actually have to live with this, and this is one of those things where I'm going to show some of these to you, and you're going to actually look at some of your photos, and it might ruin those photos. Not ruin the photos, but you might start to realize some of the issues with your camera. But it's kind of important to realize it, because if you don't notice it, maybe someone else will. So the first one are spherical aberrations. And so if lens elements within the lens as a whole are actually made with if you imagine like a sphere and you sort of chop off a portion of that sphere, that would be a spherical lens element, and that actually does not properly focus light on the edges compared to the very center. So the rays do not actually converge at the same point at the outer edges of those compared to aspherical lenses, which have a shape that try to overcome this issue. So aspherical lenses they're not spherical, and they have more of a tapering sort of at the edges of the lens to try to overcome this issue of focusing the rays too strongly at the outside edges of these. So typically what will result, so if you imagine this concept of the circle of confusion, if it sort of matches this sort of narrow band here, well, you can imagine that we will have some areas of it that actually are out of focus. It will actually appear as though there's some fuzzy areas in your photograph. Now similarly, imagine that we have some light that comes not straight on, but off axis. So it's not actually on the same axis as the lens itself is pointing. We can get this interesting result called a coma, which is sort of like the word for comet, because that's what it actually appears like. So the image, which we can see here in the very middle portion, is that we might have a point source of light that actually sort of spreads out, and it looks like it has a tail, like a wide, diffuse tail, as a result of some imperfection in the lens. You can sort of trace the rays of light as they actually enter this lens and are from the outside compared to the innermost parts of this lens, and you can sort of see why this might actually be happening. And there's a couple of different diagrams here to try to show you why this might be happening. But what this would actually look like in your image is this. So you have an image. This center portion along the top here is a single image, and we are cropping 3 distinct portions of that image from the very center and also at the very outside. And we can see how these point sources of light actually look different in each of these areas. So in this case, we have the very center, a point source of light that's coming on axis. It's coming head on, so the light rays are actually converging properly, and it looks correct. It actually looks like a single point source of light. But as soon as we get to these objects that are off to the side and they're coming at a slightly at an angle to the axis and not head on, then we start getting some of these issues, and we can see this sort of smearing, this coma that can result as a result. And so again, the outside of our image is the problem here, and also the fact that we might be able to fix this by stopping down a couple of stops on our aperture by making our aperture smaller. But that's how we would potentially fix this. But again, it's not always necessarily possible. Now, for those of you that wear glasses or contacts, you may be familiar with the concept of astigmatism, which also applies to lenses as well. And in this case, If you are astigmatic like I am, things that should have some particular shape are in fact distorted slightly, but in such a way that it's not really like super obvious. It will stretch a circle, for example, to make it a little bit more of an ellipse. It will distort a square to make it slightly less square and more rectangular, those sorts of things. And this can cause some interesting out of focus areas as well. We might get some sort of weird diffraction pattern in our out of focus areas, which would impact our bokeh, and a variety of other patterns that we can see here. But usually we would notice this mostly in the out of focus areas and not quite so much in the actual geometry of the shapes that are within our scene. But this is just something that does happen as well. Again, this isn't really something that I would worry too much about, because normally it's not quite so bad and as obvious as this. But this is one of the reasons why you may not have a perfectly smooth bokeh in your out of focus areas. Now, vignettes is something that has come back into vogue a little bit in recent years, thanks to things like Instagram, where people intentionally try to add some darkening to their corners. This is an extreme example of that, where we have a vignette that's actually blocking out the light from the corners of this image. But I mentioned this because there's actually a variety of types of vignette to watch out for. There's optical, there's mechanical, there's also natural vignette. And sometimes it's important to understand the distinction of these, because some of these you can actually correct and some of them you cannot. So let's first look at an optical vignette, which in this case is due to a lens that has a really wide aperture, and lights that comes in through the side is not actually going to be is going to be physically blocked by the actual side of the lens. So imagine we have this lens here. You can sort of see what happens if we are looking through the lens just off axis very slightly. No longer do we see behind the lens in a circular way as we normally would, but we see this sort of cat eye-like formation. And again, stopping down would actually fix this issue. But we actually saw an example of this from one of my own images a few weeks ago, where out of focus areas in this image actually have this optical vignette as a result of this wide aperture that I was using with this lens and the light coming off axis as a result of that. So as you might recall, when I sort of discovered this live, that I was sort of surprised to find it because I'd never noticed it before, and it kind of annoyed me that this actually happens, but it is what it is. I guess I would have to get a different lens to actually be able to overcome this. Of course, stopping down might be a possibility, but in this case it simply was not. I had to use the widest possible aperture in order to actually get this image because of how dark it was, and the fact that I was using it at full zoom. This was at 200 millimeters, 35 millimeter equivalent, and using it handheld on a boat that was moving, so I had to make sure that I tried to get the maximum possible shutter speed. Now we might get a natural vignette, which is actually, which despite what it looks like is not really due to light fall off, but is in fact due to micro lenses. So imagine that we have a lens that has a very small focal length, in which case the light comes at very strong oblique angles, particularly to the sides of the sensor. What can happen here is that the micro lenses may not be able to properly focus the light that's coming from this lens into the pixel, and so we might get some sort of natural vignette as a result just in the corners of this image, especially in wide-angle lenses. You notice this especially in wide-angle lenses. With longer lenses, the light tends to come in at a lot more parallel angles, and so it sort of reduces the possibility of this. But as you saw, longer lenses might have some other issues with optical vignetting. All right, so there's some other ones as well. Probably the one that you most likely have noticed in your own photographs are barrel or pincushion distortions. So imagine that if you take your photograph, print it out, and wrap it around a barrel, that's the kind of distortion that you would get in barrel distortion. It will make lines sort of bulge out towards you. Pincushion distortion is sort of the opposite. Imagine that you put it on a pillow. You put your photograph on a pillow and you push in at the center, and all the lines sort of converge inwards. That would be pincushion distortion. And this becomes very, very noticeable. Typically what you find is that wide-angle lenses have barrel distortion, telephoto have pincushion. Normal lenses can sometimes get away with this, with these particular types of distortions. You can correct them easily in software, fortunately, especially software that knows your lens and your software, or your lens and camera combination. But here are some pretty bad examples. On the left, we have some barrel distortion. This window, notice in particular at the very bottom, seems to be bowing outward like it's wrapped around a barrel. And the building here, although at first glance looks pretty good, you'll notice that it actually kind of gets squeezed in the middle due to some pincushion distortion. This is really found, this is really prevalent in consumer-grade cameras, the ones with fixed lenses. Fortunately, what we're seeing in technology these days is that the lenses and the cameras will actually automatically correct for distortion with known lenses connected to them. So we're actually seeing a reduction in some of the optical distortions, such as this, that come out of our cameras as a result. But still, the lenses probably still have these issues optically, even though we may not see them digitally. So there's another one as well, which is when we think about the light, the wave property of light, we can actually get artifacts due to refraction, which is very similar to the way that we would have a prism like this, which actually takes white light and separates the light, because the light is actually changing, the different wavelengths are changing speeds within the material. After we have a change in material from light, from air to glass, the refractive index changes, and so it sort of splits it all off. Just a similar way that a prism actually works. The light is actually changing speed within this medium, and then once it comes back out to the other side, it sort of resumes, but not without some error in the angle. And this actually impacts lenses as well, and one of the things, we've just really been totally ignoring this, but this can cause some chromatic aberrations within our photographs. Imagine that we have a simple lens, like on the left. We will actually see that the blue light focuses first, then the green light, and then the red light. Of course, it's a spectrum, but what this would actually look like is some blurring within your image. And this is especially bad on the outsides of the sensors, where the blue sort of focuses furthest out due to these refractive problems. And without correction, this can actually cause some pretty bad problems. We can actually see this in an exaggerated version here, where we have this sort of blurriness that results, but really you can see that it's like the lines have this spectrum of color because of the light that was split. So if you sort of imagine this in the context of a black and white image, this would just look like pure blur. It would look perhaps out of focus, or it would look like there was some issue there. And this is one of the many reasons why it's really difficult to get a really high quality black and white image, is that any one of these sort of aberrations can really just come across as blur in your black and white image, whereas in the color image, we can sort of distinguish between some of these aberrations. Now, some more aberrations are, of course, purple fringing, which is really prevalent on some combinations of cameras and lenses. And this might be the case that it is actually a poor lens. It's actually not refracting the light properly. But normally, what we would see in digital cameras especially is that the camera would have micro lenses that was really only optimized for green wavelengths, and so the red and the blue wavelengths would be improperly focused, and we would get this combination. We'd get this like purple fringing that would result because of that. There's, of course, ways to fix this. Stopping down will sometimes help, because then that means that color won't come in at such an oblique angle, but also the lens itself, if it uses some material like fluorite, which really sort of reduces the problems of of diffraction, then you might actually have this, or refraction, excuse me. So there's other things as well. So we have a diffraction. So I was using before we were talking about refraction, but diffraction is basically when something behaves as a wave. This can be water, this can be light. When it works its way around an obstruction, we actually get these patterns of constructive and destructive interference, where we can actually see that even though we have waves that are coming at this angle from left to right, as soon as it hits this obstruction here, as the waves work their way around that obstruction, there are waves that continue along, but we also get these phases of destructive and constructive interference where that wave then propagates incorrectly after that obstruction. And we can actually, so one way that this would actually appear is that if we have a point source of light, we shine it through a really small hole, we might actually get some diffraction. We wouldn't get a perfect representation of that, but in fact we would get this sort of airy disk, concentric circle appearance. And this, if it exceeds, of course, the circle of confusion, would result in some blurriness in our image. So just to sort of show you one issue here is that as you make your aperture smaller and smaller and smaller, that it's actually causing a small obstruction in this way. And once you get close enough to some multiple of wavelength of light, you will actually get to this issue where you'll get diffraction that causes all sorts of softness. So even though we have an image that is technically in focus, we have some diffraction issues that are softening all of the light that's actually coming into the camera. And so given this very small pixels that we have in cameras these days, you really will find that even modest increases in apertures, such as f11 or f16, will cause diffraction, softness due to diffraction, especially on much smaller cameras. So this has been a lot of just sort of a whirlwind tour of optical aberrations that can actually happen and impact the image quality of our camera. But there's also some digital artifacts that can actually result. We've actually gone over some already. We've talked about posterization, what that actually is and what it means. You might recall that was, we had that photo of the sunset. We increased the contrast to such a degree that no longer was there a smooth gradient from blue to black, but instead it was steps from blue to cyan to black. And that was an extreme example of posterization. We've also talked about noise at length, where increasing ISO, which is not quite the same as actually changing the sensitivity of a sensor, will change the noise that comes out of that sensor, and also some blooming, which can happen when photons actually overwhelm individual pixels and spill over to neighboring pixels, and we see not just a small area that's overexposed, but a much larger area than we would actually expect. But there's some other digital artifacts as well. We've talked about some of these as well, like aliasing and anti-aliasing, where we can actually change we would actually get smoother edges, but we actually do get some loss of resolution. The context for this, of course, was the anti-alias filter, the low-pass filter that exists on the top of many Bayer color filter array cameras, the sensors of those cameras. And there was Moira as well. There's just a couple more examples of that where we take this, and this you might actually find this outside of the context of just simply taking a photograph, but if you were to have an image such as this, which has a somewhat high frequency repeating pattern, in this case the alternating red and white between the brick and the mortar, and you change the size of this image, you actually resize it to be smaller, it's actually very difficult for the computer to represent that same pattern if some of those pixels drop below 1 pixel, if it should actually become smaller than 1 pixel, and if it can't actually replicate that same pattern in the smaller size very well, you'll get this sort of strange repeating artifact, this Moira artifact, because some pixels will be essentially rounded up and some pixels will essentially be rounded down. Now, the reason that you would see this is if repetitive detail sort of exceeds the resolution of the sensor or of the image that we're actually creating, which in this case the repetitive detail does once we've rechanged the size of this image to be smaller. Then we also talked about Moira and maze patterns, where we can get Moira, but also in combination with some strange maze patterns as a result of this the demosaicing algorithms that occur when we have a color filter array and we're reconstructing that image. One of the things that we really didn't get a chance to provide many examples of, however, were sharpening halos. When you take an image and you're trying to combat this issue where you have a somewhat, the focus might be ideal and you might have a somewhat sharp image, you want to reduce the softness even more. You want to make that image even sharper to try to counteract your anti-aliasing filter that probably exists in your camera. You might actually be tempted to use a sharpening tool that Lightroom or Photoshop or some other software actually has. But the way that these tend to work is that it finds areas of contrast, such as the interface between this circle and the background, and will try to increase the contrast between the two of them by taking the darker edge and making it slightly darker, and taking the brighter edge and making it slightly brighter. And if you go too far, you'll actually get this halo appearance, because the inside is now too dark and the outside is now too bright. So there is definitely a good middle ground between when we have too soft and when we apply some sharpening so that we actually do get some nice amount of definition back, and when we overdo it and in fact increase the sharpening to such a degree that we get some halos. So if you are in fact going to apply some sharpening to your image, take a look around at a variety of places, not just one place, but zoom in to 100% and make sure that you haven't overdone it and gotten some strange halos such as this. You can really help out your case by using RAW, of course. That will help to sort of fix these. Also, what you will find is that if you use JPEG by default in the camera will automatically apply some sharpening, and some cameras will go so aggressive that they will in fact give you for free some halos, and that's probably not what you want. So be mindful of that, use RAW when possible, and then you can define for yourself exactly how much sharpening you want out of your image. And when we're talking about compression, we talked about, at the very beginning of the semester, we were talking about the lossy compression of JPEG versus lossless compression of other file formats such as PNG or PSD. And really, we can get some compression artifacts out of that if we, of course, use quality that is a quality measure that is just far too low. So the compression will discard some color information. It will discard fine detail based on some measure of our perception of how we would actually perceive that. So when you're working on images, what I would recommend is try to have a non-destructive workflow. Try to take photos in RAW. Use some software like Lightroom or some other RAW processing software that allows you to apply changes, but doesn't actually finalize those changes until you export into a lossy format like JPEG. That way, no matter how many times you open that file and change it, and then resave your changes to that file, you can then receive the highest possible quality out of that image. If you were to take an image, a JPEG image, for example, out of your camera, make some modifications to it, save it, go back, make some more modifications to it, save it again, the lossy aspect of JPEG will, in fact, change this image over time. Now, there's sort of a little asterisk here. If you just open a JPEG file and save it and save it and save it, just keep opening it without actually doing any other modifications, most JPEG saving algorithms won't actually change the image for the worse, so you should actually be able to do this over and over again, but some will, so just be mindful of that. And again, you can get around all of these issues by just using RAW and using a non-destructive editing format. So with all of these, hopefully you'll be able to be aware of some of the artifacts and some of the problems that you can have. Hopefully you're a little bit more knowledgeable about color information, why it's actually important to profile your monitor, and hopefully that will be a good starting place as you work on your final projects, which of course are due next week. And until next week, I want to thank you all very much for coming, and enjoy the rest of the week, and we'll see you then.